Welcome back to the channel. Today, we're diving deep into Spanning Tree Protocol, or STP. If you've ever wondered how switches prevent network loops while maintaining redundancy, this video is for you. We'll walk through exactly how STP builds a loop-free topology step by step. Let's get started. Here's our sample topology for today. We have 4 switches, SW1, SW2, SW3, and SW4, all interconnected to provide redundancy. We are assuming default values. No customization has been done on the switches. The switches are connected via fast Ethernet interfaces. This redundant design is great for fault tolerance, but without STP, we'd have a serious problem: broadcast storms and network loops. That's where STP comes in. Building an STP topology involves 4 key steps. First, we have root bridge election. This determines which switch will be at the top of our spanning tree. Second, we have locating root ports, where non-root switches pick their best path to the root bridge. Third, locating blocked designated ports. This is where we prevent loops by blocking redundant connections. And finally, verification of VLANs, where we confirm our STP configuration using show commands. Let's break down each of these steps in detail. Before we dive into root bridge election, we need to understand STP path cost. This is crucial because STP uses cost to determine the best path to the root bridge. Looking at this table, you can see that slower links have higher costs. A 10 megabits per second link has a cost of 100 in short mode and a whopping 2 million in long mode. A 100 megabits per second link costs 19, while a 1 gigabit per second link costs just 4. The fastest links, 100 gigabits per second, have a cost of only 1. Think of the cost as the price you pay to traverse a link. STP will always choose the path with the lowest cumulative cost to reach the root bridge. The root path is calculated by adding up the interface costs along the way to the root. Long mode was developed as switches got faster and needed more granular cost values. In our examples today, we'll be using short mode costs. Now, let's apply this to our topology. Since all our links are 100 megabits per second fast Ethernet connections, each port has a cost of 19. Look at SW1. It shows a root cost of 0. Why? Because SW1 is the root bridge. You don't pay a cost to reach yourself. SW3 shows a root cost of 19. That's because it's one hop away from the root bridge through a single 100 megabits per second link. SW2 also has a root cost of 19 for the same reason. But look at SW4. It has a root cost of 38. That's because the shortest path from SW4 to the root bridge is through 2 100 megabits per second links. 19 plus 19 equals 38. These cost values will be critical in determining which ports become root ports and which become blocked. Now, let's talk about how the root bridge is elected. When switches initialize, each one assumes it's the root bridge and advertises its own bridge ID, called a BPDU, Bridge Protocol Unit. Then the fun begins. Each switch listens for neighbors' BPDUs. If a neighbor's BPDU is superior, the switch updates its idea of who the root is and starts advertising that new root's ID instead. But how do we determine superiority? That's where the tiebreaker rules come in. First, the switch with the lower priority wins. Lower is better in STP. Think of it like golf scores. If priorities are equal, we move to the second tiebreaker, the MAC address. The switch with the lower MAC address becomes the root. Again, lower is preferred. This process ensures that the entire network converges on a single root bridge. Let's see this in action with our topology. All our switches have the default priority of 32,768, so we need a tiebreaker. Looking at the MAC addresses, SW1 has 1.1.1.1, SW2 has 2.2.2.2, SW3 has 3.3.3.3, and SW4 has 4.4.4.4. Since SW1 has the lowest MAC address, it wins. SW1 becomes our root bridge. Notice what happens to SW1's ports. They all become designated ports marked as DP in red. This is a fundamental STP rule. All ports on the root bridge are designated ports and forward traffic. They never block. The root bridge is the reference point for the entire spanning tree. Every other decision in the topology is made relative to this root. Now that we have our root bridge, all non-root switches need to determine their root ports. The root port, or RP, is each switch's best path back to the root bridge. But what makes a path best? STP uses a hierarchical set of criteria, and we only move to the next criterion if there's a tie. First criterion, the interface with the lowest path cost is preferred. This makes sense. We want the cheapest route to the root. Second, if costs are equal, we prefer the interface connected to the switch with the lowest system priority. Third, if that's also tied, we use the system MAC address. Lower is preferred. Fourth, if we have multiple links to the same switch, we prefer the interface with the lowest port priority. And finally, fifth, if everything else is equal, we choose the lower port number. These rules ensure every non-root switch can definitively choose exactly one root port. Now, let's apply these rules to our topology. Remember, all non-root switches, that's SW2, SW3, and SW4, must elect root ports based on path cost. Look at SW2. It has a direct connection to SW1 via F0/4. Using short mode, the cost for a fast Ethernet port is 19. Since SW2 has only this path to the root, F0/4 becomes its root port. SW3 is similar. It connects to SW1 via F0/1 with a cost of 19. F0/1 becomes SW3's root port. Now, SW4 is more interesting. It has two potential paths to the root. Through F0/3, it would go SW4 to SW2 to SW1, that's 19 plus 19 equals 38. Through F0/2, it would go SW4 to SW3 to SW1, and that's also 19 plus 19, which equals 38. We have a tie. When we have a tie in path cost, we move to the third criterion, the lowest MAC address of the advertising switch. F0/3 connects to SW2, which has a MAC address of 2.2.2.2, while F0/2 connects to SW3, which has a MAC address of 3.3.3.3. Since 2.2.2.2 is lower than 3.3.3.3, SW4 selects F0/3 as its root port. Lower MAC address wins the tiebreaker. All unassigned ports will be changed to the designated state in the next step. With the root bridge identified and root ports selected, we still have one critical task: preventing loops. This is where designated ports and blocking ports come in. After the root bridge and root ports are identified, all other ports are considered designated ports. But here's the catch. If two non-root switches are connected on their designated ports, one of those ports must be set to blocking to prevent a forwarding loop. The logic works like this. First, the interface is a designated port and must not be considered a root port. Second, the switch with the lower path cost to the root bridge forwards packets, and the one with the higher path cost blocks. Third, if path costs are tied, we compare system priorities. The lower one forwards. Fourth, if priorities are equal, we use system MAC address. The local designated port goes to blocking if the remote system MAC address is lower. This ensures every segment has exactly one forwarding path. Let's see this in action. Look at the segment between SW3 and SW4. They're connected via their designated ports on F0/2. Remember, SW4's F0/3 is already the root port, so it's off the table for blocking. That leaves F0/2 on the segment between SW3 and SW4. Now we compare the path costs. SW3 has a path cost to the root of 19, while SW4 has a path cost of 38. Following our first criterion, the switch with the higher path cost must block. Since SW4 has the higher cost, 38, versus 19, SW4's F0/2 transitions to blocking state marked as BLK in red. This breaks the loop while maintaining redundancy. If SW2 or the link between SW4 and SW2 fails, STP will reconverge and activate that blocked port on F0/2, routing traffic through SW3 instead. This is the beauty of STP, automatic loop prevention with built-in redundancy. And that's how STP builds a loop-free topology. We covered route bridge election based on priority and MAC address, route port selection using path costs, and blocking port designation to prevent loops. Understanding STP is crucial for any network engineer working with switched networks. In a future video, we'll cover RSTP, Rapid Spanning Tree Protocol, which converges much faster. If you found this helpful, please hit that like button and subscribe for more networking content. Drop any questions in the comments below. I'd love to help clarify anything about STP. Thanks for watching, and I'll see you in the next video.